Hello, good afternoon, and welcome to the Great Exhibition Road Festival. It's wonderful to see so many of you here in the audience. My name's Mitchell Clark, and I'm the Programmes Manager here at the Royal Geographical Society. In this grand lecture theatre, we've spent 2 days celebrating ideas, technologies, and individuals that have contributed to our modern world and could influence its future. In this final session, we are taking the trailblazing spirit off-world with a report on the latest findings from NASA's Perseverance Rover and its groundbreaking search for evidence of possible Martian life. To tell this story, we are delighted to be joined by Imperial College London's Professor Sanjeev Gupta, a member of the scientific team directing the rover's search for rocks and evidence of possible Martian life. Before I hand over to Sanjeev, I'd like to remind everyone that this is an interactive session and there'll be plenty of time for questions at the end, so do get thinking of any. So I'd like to hand over to Sanjeev.
Gosh, there's quite a lot of you. I'm a little bit nervous now. Not really. Welcome on this lovely afternoon to the Royal Geographical Society and the festival. It's amazing to talk here, given this has been the center of discussing explorations on Earth, and now we can get to explore our solar system. And I'm going to tell you about Mars. And I should say, firstly, that I'm an accidental planetary scientist. I'm actually an Earth scientist who mostly spends his time working on Earth, and my research encompasses, water problems in India, searching for water, how Britain became an island. So the last time I gave a talk in this hall was actually about what lay under the sea, and I've subsequently moved into working on planetary things. So I'm going to talk a little bit about 2 missions, mainly about the most recent mission, the Perseverance Rover mission, and tell you about the search for ancient life on Mars. I realize the slides are there because it's really awkward to look up there. And firstly, I should say that I'm really representing a very, very large team. So it's not me alone that does this. To operate a robot on Mars requires almost 200 to 300 engineers, and there are 500 people on the science team to work out what we want to do and to analyze the data. So it's a huge team effort, and it's a very different form of science working in these large teams. And I've just come back from last week where I was in Los Angeles and Pasadena at our first science team meeting where we could actually get together. We've actually been operating this rover for about a year, and about half the people on the team I'd never met before. And we've been doing it all remotely because of COVID, etc. So what was Mars like? Mars today is like the left-hand image over there, cold, dry, and dusty. It looks red and it looks hot, but it's not. There's actually an app where you can get the temperatures on Mars, and I will tell you that the temperature in Jezreel Crater currently is about, the highs are about 1 degree centigrade, and the lows are about minus 71 degrees. So it's not you're better off here, basically. But if you have the ability to travel back in time, if any of you do, please tell me, because I'd like to know. But I do it in my imagination. If you were to go back about 3.7 billion years ago, Mars was likely to have been warm and wet and had an atmosphere. And the surface was covered in lakes and rivers. And some people even think that there was once an ocean on Mars that covered the northern plains. That's a very, very contentious hypothesis. We really don't have any clear evidence for that. It's an idea. It's a nice idea to believe in, to think that we could have actually once sat on the shoreline on a nice sunny day. So what's surprising to you maybe is about 100 years ago, people actually thought there was an advanced civilization living on Mars, which seems quite astonishing to us. But from telescopic observations, there was an Italian astronomer called Schiaparelli who had observed linear features on the surface of Mars, and he interpreted these as rivers. And then this was taken up by an American astronomer, Percival Lowell, who misinterpreted the Italian for small streams, canali, as canals, and he constructed this amazing story. It's one of the most wonderful stories in science at the turn of the previous century of how the Martians were living in a dying environment with many parallels to us. the climate was warming and the water was drying up, and they had constructed these amazing canal systems from the poles to the equator to transport water for the Martians who are living presumably underground. And so the next slide is perhaps one of my most favorite newspaper headlines of all time, which is from the New York Times, which is quite a reputable newspaper, as you know, well, mostly, sometimes not. And this is from a headline in the New York Times from 1911. So take a little bit of time. So people genuinely believed this, and this was because Percival Lowell did science by press release, so he would tell about his latest findings to the New York Times directly without publications, and he was observing changes in dark light patches on Mars. Eventually, it was shown actually by some scientists in Greenwich in London that this was actually all an optical illusion. So this was not true, and there was no advanced civilization living on Mars, but this was what the current thoughts then were. So beware of what I say, because it's really historians who decide what science is right, not scientists in the present day. Okay, I'm going to jump a bit, because otherwise I could be here forever. I want to talk first about the Curiosity Rover. So I'm very fortunate and very, very privileged to work on 2 robots on Mars. As my daughter refers to them, they're my robot children opposed to my real children. These ones are far less trouble, as you can imagine. Curiosity is 10 years old. She's going to celebrate her 10th anniversary this August, and it's quite extraordinary to think that she's been on the surface of Mars for 10 years. And these robots are a little bit like celebrities in that they spend most of their time taking pictures of themselves. But this is mostly for health and safety and to get beautiful images. And I think there's something about, I know we see these beautiful, desolate landscapes on Mars, but to see a human-made object in that landscape makes that feel quite extraordinary, that sort of human endeavor and the fragility of it all, that you've got this lonely little rover sat by herself in this vast crater on Mars over here. So Curiosity has been on the surface of Mars, and you can see here it is pristine on Sol 84, so Sols are a Martian day. You can see the pristine surface of the rover, and this is a few sols later, 3,070 sols later, and you can see how dusty the rover is. But most of the rover is still working, and we're doing beautiful science and making amazing discoveries. Unfortunately, everybody's interested in the new kid on the block that I'm mostly going to talk about. But I want to show some of the pictures that Curiosity, and I think you should see, look, there's a nice drill hole that Curiosity has made in these rocks over here. So the purpose of Curiosity was to discover whether there were places on Mars that it was habitable for life in the ancient past, so not in the present day. People don't think that Mars is habitable in the present day. Who knows, maybe in the subsurface, deep underground, but we can't access that easily. But at a time when Mars was warm and wet, 3.5 billion years ago, and that's when life got going on Earth. So they're kind of parallels. Did life arise in both our 2 separate planets at the same sort of time? So what we need is evidence for persistent liquid water, key chemical ingredients for life, and the energy for metabolism. And that's what Curiosity's tasks were to discover. So I'm really going to talk about water. And you can see this sort of beautiful landscape. So what Curiosity has discovered is that there were lakes present on the surface of Mars that lasted hundreds of thousands, if not billions of years. And we do that by looking at the rock record. We see features in the rocks that tell us. It's sort of like being a detective, basically. So I'm a geologist, and it's like being a detective. You look for clues as to who did the crime. Was water responsible for the crime? So the rocks you can see here in the foreground, these light-toned rocks over here, these are actually rocks. You can see that this looks like a very barren, desolate place in the present day. But if you could go back in time, this would be a watery environment, and you would have had a lake here. But interestingly, the rocks over here, we've now driven past these rocks. We drove through this valley over here, through this gap over here. And these rocks are actually all ancient wind-blown dunes, so like the ancient Sahara Desert. And so somewhere between here, there was a change in climate. And we also had a change in mineralogy. So the rocks down here contain lots of clay minerals, which are water-rich rocks. Clays form from the interaction of water with rocks. And then we go into sulfate rocks, so different mineralogy, which record a decrease, an aridification, a drying out of the climate. And we don't know whether this was global on Mars or just local, but it's an important goal to chase about ancient climate change on Mars. Because if it was a global thing, maybe that's what was the difference. That's where Mars completely lost its water, whereas Earth had a different trajectory. So one of the reasons to go to Mars is actually to help us think about our own planet. It makes you think about, well, why does Earth still have water, whereas Mars lost its water? They're very similar planets. Mars is much smaller than Earth, but they live in a similar sort of part of the solar system. So what happened? What was the difference? And it's these differences that help us think carefully about our different trajectories. So this, again, just shows you the beautiful, beautiful landscapes. And in particular, these are some new results. There's this interesting rock over here that I'm studying at the moment called the Prow, and this is a little lens of rock. And most of these rocks are ancient wind-blown dune deposits, but actually, when we look in detail in the Prow, we have a little period of water present, and I want to show you how we interpret that. So if we go and look at this, this is a section, a vertical section. That scale is only 10 centimeters through this rock. So we're looking at a segment here of that rock. And these lines that you can see here are where the dunes have migrated through time. But if we look here, you can see some little ripple-like features in here. These features over here are, we think, formed by waves in a little shallow lake. So what happened was that most of the time the environment was dry, and then maybe there was rainfall in this desert, or there was snow melt, and a small lake formed, and the wind blew across that lake, forming ripples on the surface of the lake, like you see on the sea or on the lake. And the movement of those waves actually moved the sediment at the base of that lake, which was only shallow. This is only it was only about a meter to 2 meters deep. And the evidence of those waves, moments in time, seconds in time, were preserved in the rock record, fossilized in the rock record. And I think that's quite remarkable that we can see moments of time preserved in rocks that are 3.5 billion years old on Mars. Okay, so I now want to go and talk about the new kid on the block. So most of the talk about this is the new kid on the block, but I didn't want you to forget Curiosity. So the Perseverance Rover landed in February of last year, which has been there over a year now. And this is doing something very different. We can do wonderful things with rovers on Mars in terms of robotic exploration and lab experiments, but we can't analyze the rocks in the same way that we can do that on Earth. And most scientists believe that we're not going to find life on Mars, evidence for life on Mars, through robotic analysis. We need to bring those samples back. So what this rover is doing is it's actually collecting samples for future return to Earth. And I'm going to talk quite a lot about that. So our first task is geology, to characterize the area we're going to, because obviously we're looking at rocks. And then astrobiology. Astrobiology is the science of life elsewhere. Obviously, we haven't found life elsewhere, so it's a theoretical science, if you like, but it helps us guide the position. So this is not, as you can tell from the presence of this nice advanced vegetation on Mars, this is actually in the Pilbara in central Australia. And this is what we would love to find. It's very unlikely we will find this, but you can see these dome-shaped features here. These are built by microbes in an ancient sea in Australia. And these are some of the oldest evidence for life on Earth. These are about 3.5 billion years old. So these are the same age rocks as we're seeing in Jezreel Crater. And you can see what's happened here is that there were microbes on the seabed, and they trapped sediment on the seabed. And so what you're seeing is layers of sediment being trapped by sticky films of microbes. Yucky sticky films. Would have been horrible to walk around here, but they preserved that evidence. This is in Australia, and I'm going to show you some pictures from South Africa now. So here's some more examples. These are actually in a land environment. You can see a pebble here, and overlying the pebble, you see these layers. And again, these are sediment layers that were trapped by sticky microbial mats. And again, you can see multiple layers built up over here. And if we look at a thin section, we look at a rock section through this, we can see our rock layers with our pebbles, and the black films here are our microbial films that are preserved in these very ancient South African rocks. And this is what we are looking for. This is what we would love to find. We haven't found this yet. And it's unlikely that we would see macroscopic evidence in the rocks themselves. But if we bring samples like this back, we might see chemical signatures. And it's most likely that we will find chemical signatures of life if we're going to find life at all on Mars. So I want to talk about how we go about doing that search. So this is just a cartoon of the rover, Perseverance. It looks very similar to Curiosity, but it doesn't have the very advanced chemistry instruments, because we'll do those experiments when we come back to Earth. So just to talk about the different instruments, firstly, we have the eyes of the rover at the top. We have the Mars-Cam-Z cameras. I'm on the Mars-Cam-Z team, so those are the cameras that we use for geology. But next to those, we have the navigation cameras, which are probably the most important cameras, because those are the eyes of the rovers. That's what we use to plan our drives. We have a laser at the top over here that does sort of semi-quantitative geochemistry. So what we can do is we can shoot this laser about 7 meters, and it produces a plasma in the rocks, and there's a spectrometer where you can measure the elemental composition of the rocks. And it tells us approximately whether the rock type is changing, etc. We have this very monstrous arm over here, and we have 2 instruments, Sherlock and Pixel, which are important geochemistry instruments, but we also have the whole drilling system to collect the samples. And we have a weather station, MEDA, and we also have some subsurface radar to tell us what's going on underneath. So this is a bit of street art. A colleague of mine found in the city of Lyon. So you can see, maybe we'll find some of these early Neanderthals on Mars. Very unlikely, but I love this image. How would Perseverance react? Probably with its laser, I think. Okay, so this is Perseverance in the clean room as it was being built, and this is being the turret being assembled over here. And we can see the turret is huge over here. These are the stabilizers, so when the turret is placed on the rock surface for drilling, those are the stabilizers, and the drill bit comes out of here. And what's amazing is what's actually inside the belly of the rover, and this is what's inside. This is what we call the ACA. It's the sample handling facility. This is where we store the samples. So this is, if you like, a very, very expensive rucksack. That's as very simple as that. Obviously, the trendy rucksacks are also very expensive, but this is, if you like, I won't mention any names, but here we go. So this is where we store our samples once we collect them. But you know what? We have a problem here. We have a very, very big problem. How do we select the samples to carry? When I do field work, and I do field work in remote places, for example, in the Alps, really high up, so about 3,500 meters, and I find a nice rock, I sling it in my rucksack, and I carry on walking. Maybe a little bit later in the day, I might find an even better rock, and I want to carry both rocks, so I'll sling the one I had out earlier out and put the new rock in. We can't do that. We've got 42 tubes. Once we've collected a sample, that's it. So you have this problem of, do I collect the sample now, or do I wait for another sample that might even be better, but I don't know what it's going to be? And that's the dilemma we often face. Actually, we just collect the samples in general because it's quite hard collecting samples. We've been having lots of problems recently because the rocks keep breaking up. And if you always worry about, should I collect the one further along, you'll not collect any samples. And you'll get to a sudden stage where, oh my goodness, I need to have all my samples, and I don't have any samples. So, but it's an interesting problem to have. So this is the arm, and it puts this in here. And what will eventually happen is that the samples will come out of this and will be deposited on the Martian surface for future collection, and I'll talk about that in a bit. So we have 38 tubes for rocks and regolith over here, and we've already collected about 8, I believe, something like that. And we have 5 what we call witness tubes. These are just empty tubes that sample the current surroundings, and those are just to make sure that we have no contamination, or to understand what the contamination levels are, because we're trying to, obviously, the main question we're trying to answer with these samples is, did life occur on Mars? And so we don't want to have to take the life to Mars to do that. Okay, so where did we go? So this is a topographic map of Mars. This is where the Curiosity Rover landed in Jezreel Crater, and this is where the Perseverance landed in Jezreel Crater. So let's take you there. It's on the edge of this basin called the Isidis Basin, which was a giant impact basin formed very early in Mars's history, about 4 billion years ago. And then on the edge of that, we have Jezreel Crater over here, which is actually named after a lake in Bosnia, Jezreel. We pronounce it completely wrongly, unfortunately. My Bosnian friend is very unhappy with me about that, but it's already embedded. So this is the crater over here, and the reason it was chosen was, firstly, scientists believed it held a lake once, 3.7 billion years ago. And the reason we think this is that we can see a valley network, a valley coming into it, a river valley coming into it, and a valley going out of it. So water must have filled the lake and then gone out. And at the mouth of this, we have a feature, a sedimentary feature, which we think was an ancient delta. So you can see this is an imagination of what it would have looked like, and it must have been a wonderful place. And if you'd been around 3.7 billion years ago, 3.5 billion years ago, you could have gone and had a picnic by here, with cucumber sandwiches or whatever you fancy, and a sausage roll. Would have been lovely. But anyway, that's our idea, and that's what we've been testing. And lakes, we search for lakes, ancient lake sediments, because astrobiologists believe that lakes are good places for life to have formed in and to have existed in. So some of you will have seen all the beautiful movies of the landing sequence there, animations, but basically the spacecraft took 7 minutes to land, and this was all done automatically. But I love this image because it's actually a rather geeky image of one spacecraft taking a picture of another spacecraft landing. So this is from the MRO orbiter that goes around Mars, which has this fantastic camera called HiRISE, and it took a picture of Perseverance landing with the world's biggest parachute up there. And in this sequence, you can see they put some GoPro cameras basically on the rover as it was for the landing sequence, and you can see the parachute unfurling here, I hope. There we go. There's a nice little story about this. This parachute was actually made in Tiverton in Devon. There's a specialist firm that makes the parachute fabric for most missions, actually. And then here's the heat shield coming off, and then they took a sequence, the GoPros that were looking down, took a sequence of images as it was lowered onto the surface of Mars on these nylon tethers. So you can see, here we go, being lowered down onto the surface of Mars. Here's the wheels unfolding, and the dust comes up, and then it was on the surface of Mars for us to get into action. And we landed over here in this location named after this very famous science fiction writer, Octavia E. Butler. And our goal was to basically drive onto the delta to investigate, firstly, the rocks of the crater floor, the delta, and subsequently we're going to drive, we're over here at the moment, subsequently we're going to drive onto the delta, through the gap, through the river valley, and then outside the crater to explore the really ancient terrain that lies beyond the crater. These rocks are older than anything we have on Earth, and that's going to be amazing. So actually, another reason to go to Mars is that we might learn something about our planet that we don't have on Earth, because the most ancient rocks on Earth are destroyed. They're preserved as tiny crystals, as zircon crystals, but the actual rocks themselves are not preserved. but rocks of a similar age that record the earliest history of planets, solid planet, rocky planets, are preserved abundantly on Mars, and that's a reason to go there to find out about our beginnings. Okay, this is a lovely picture again taken by HiRISE. This is the rover actually on Mars over here, and the white patches are where the dust was cleared as the rover was landing. And you can see this is one of the first images of this desolate terrain. You know, I don't think I would want to go to Mars. I'm happy to send a rover. Looks pretty grim. Can't get a cup of tea up there. Okay, so we landed in this very interesting spot over here where we see the transition between two different rock types. And prior to landing, we had no idea what these rocks were, and we had many different hypotheses. One was that these were both these two different terrains in different colors. One was that these were ancient lake deposits, and the other one that had been proposed was they were ancient volcanic rocks. We were quite excited about the possibility of ancient volcanic rocks because it tells us about the deep history of Mars, deep beneath the surface, but also volcanic rocks can be dated when they come back to Earth. We can use radiometric dating. That was a technique actually invented about 100 years ago at Imperial College by an undergraduate student, can you believe, as part of an undergraduate thesis, Arthur Holmes. And that's revolutionized our understanding of Earth. We know about deep time on Earth through radiometric dating, but we want to do this for Mars, and we haven't done this for Mars. So we have a sort of relative chronology for Mars, but we don't have a proper chronology for Mars. So we don't really know how old things are precisely, and that's what we can do by dating volcanic rocks. So here's just some of our beautiful mosaics showing that terrain, and you can see this landscape. And these rocks over here, we have now uncovered, are actually volcanic rocks. So they were formed by volcanoes. We don't know where the volcanoes were, that erupted lavas that swept across the floor of Jezreel Crater. And you can see the beautiful terrain, and you can see here Perseverance's sidekick, Ingenuity, the helicopter that's done the first powered flight on another planet. So this is about 0.5 meter high, but the rotors are really big because the atmosphere is so thin on Mars. It's really high to fly on Mars. So the rotors themselves are about 1.2 meters across. You can see them here, twirling here in this little GIF. I'm just going to show you a video of one of the first flights. So watch the Ingenuity over here. What's actually more remarkable, I think, than the flight is pretty remarkable, but let's see if I can get that working. Okay, is to actually take a video of this, because this is actually taken from a very long way away, with the full zoom of the cameras, but the Perseverance and the helicopter have completely different clocks. So you have to synchronize the clocks and then point in a particular direction to absolutely capture that. So it's being pretty zippy. It's going to come back in a minute too. It does quite wacky things now, but this was in the early days. Maybe it'll come back. We could be here a while. There you go. You can see how well behaved it is, unlike some people. Okay. So we landed here, as I said, and the big problem we had was this terrain over here was not traversable. So we'd hoped to land over here to get to the delta, but this terrain was not traversable. So we spent the first part of the year really examining the rocks in this area, and we decided to drive south and explore the rocks in here to try and work out what was going on in terms of the geology of this area over here and what it meant for Martian evolution. So here's just some images to show you the sort of terrain. So this is our first Sol 4 checkout. It goes by very quickly because it's such a huge image. That's looking into the distance towards the delta. And then we have these beautiful rocks off the delta over here. And in the early days, we were actually able to make some initial discoveries about this. So I'm going to show you some details of the images over here. And we're going to zoom in on the cliff faces and zoom in even more. And what you can see is those cliff faces are made out of big boulders. Can you see these? That boulder is about 2 meters in diameter. So just imagine the scale of that. You also see that it's rounded. So most rocks that lie on the surface of Mars are angular because they've been formed by impact processes. They're meteorites colliding with the surface of Mars, and they produce impact processes. To produce rounding of boulders on Earth requires water transport. So what this tells us is that these rocks, these pebbles and cobbles and boulders, were actually moved by water, but not any water. These were huge floods, because to move a 2-meter block of rock requires enormous forces, basically. So this tells us that there were enormous floods on the surface of Mars, or at this place, maybe formed by glaciers melting or heavy rainfall, we don't know. That's time. And then below that, we can see these beautiful beds in this beautiful image taken with a SuperCam instrument. This is the Marscam instrument, this is the SuperCam instrument. You can see these large-scale inclined beds over here. This is about 10 meters tall over here. And now you won't understand the details of that. For me as a geologist, that's very special, because this is the clue that suggests to us that this was actually a delta. So prior to landing, we thought there was a delta, but that was a hypothesis. This tells us this was absolutely a delta. So let me show you a modern delta on Earth. Or we could see these inclined beds with cobbles in them. And this is what a modern delta looks like. This is in Greece, and you can see the rivers coming through here, and it's built this sediment lobe out. And then if we go, this is the shoreline over here, and if we go back here, this is the shoreline over here, preserved in the rock record. So again, if you were on Mars 3.5 billion years ago, you could have sat here at the shoreline and had your picnic. As you can tell, I like picnics. So if we were to look offshore over here, you would get a section through the delta over here. So these things we call faucets. But it's down at the base over here. These are the fine-grained deposits that we expect to find evidence for life, and that's what we're searching for at the moment, and I'll come back to that later. So what about the crater floor? So what we wanted to do was to select a place where we could sample. So we got to this place, and the engineers wanted a really flat place with no engineering issues to be able to sample, collect our first sample. So we chose this place over here where we have these sort of paving stone-like rocks. So here we are, we're doing our first abrasion. So we have a tool on the arm where we can clear the dust and weathering rinds of the surface, so we can look at a fresh surface of the rock and measure the chemistry of the rock. So this is what we're doing here. And this is the rover arm being deployed. So you can see that's really quite hefty over here. It's about this big over here, being deployed. And imagine, we don't do real-time operations. Every movement there has been sequenced, a series of commands written by the engineers for that to happen on Mars the next day. So what we do is we come into work, and it's a Mars night, basically, during an Earth day. The scientists work out what we want to do, what experiments we want to do. We then give that to the engineers. The engineers will say yes or no. They'll mostly cut, scientists say, I want to do this, I want to do this, I want to do this, I want to do this. On all of these different rocks, the engineers say the scientists are like squirrels. Here's a nut, here's a nut, here's a nut, I want everything. And what they do is they have constraints, because we may not have enough power to do all those experiments. We may not have enough time. And importantly, it might be too complex, because they have to write the commands and check the commands. As you can imagine, this is a very expensive mission, and that's really people's salaries. It's expensive because we have so many engineers who do all these very complex things. And if something goes wrong, nothing bad can happen to the rover, but we might lose several days where the rover goes into safe mode, and we have to work out what happens. And obviously, that can quickly build up in terms of costs. And so we try to make sure that everything's simple and not too complicated, that we don't break the rover, basically. So here's what you can see is, here's the abrasion patch. So basically, we rubbed away with like sandpaper, essentially, to get a fresh surface. And we drilled our first drill hole over here to collect our first core sample. And what happens is we drill, the sample is collected, and then immediately is transferred into the rover for safekeeping. So we have a camera to look inside the belly of the beast to see where we store the cameras. And we collected our first sample, and we were very delighted, as you can imagine, successful drilling. And then we looked with the camera inside the sample tube. Can anyone see a sample in there? No, it was empty. And really, not panic, but a lot of concern. What happened? Essentially, the rocks were very, very weak, and there's the sample. It disintegrated. So, gosh, that set up a lot of problems. This is our first sample. This mission is all about sampling, and our first sample disintegrates. So, as you can imagine, the engineers and the scientists were extremely concerned, and a lot of effort went into really thinking about what happened and how it happened. The end result was that we decided that rocks were very, very weak. They'd been heavily weathered, basically. So the next time, we selected a sample from a rock that looked more tough and stable, etc. So that was our first sampling. So we drove, this is our landing site over here, so we'd driven south. We drove over here to a place called Citadel, and we found this rock sample we called Rochette, little rock. And you can see it's got vertical sides over here. And so the engineers decided this was a good one to sample because it looked really firm and strong and tough over here. So with much trepidation, we went through the whole process. And here we are setting up for drilling. This is from the hazard cameras, setting up for drilling over here. And that's our drill bit over here, and the stabilizers on either side. And there's our abrasion patch, and that's our first drill hole. So again, successful drilling, but then, gosh, are we going to collect a sample again, given what happened previously? And obviously, once you've used a sample tube, you can't use it again. So our first sample was immediately turned into an atmospheric sample, because obviously it trapped some atmospheric gases from Mars. So we'll be able to analyze those once they come back to Earth. So what we did was we sampled, and then we spent a lot of time actually looking inside the drill bit with some of our cameras to see if we could see the sample in the drill bit before putting it into the sample tube inside the rover. And there it is. We could see it in the drill bit. There's our successful sample, Montagnier. And then there it is, just before being sealed. So we took that picture just before being sealed inside the rover. And the next time this sample tube will be opened is in 2033 when it comes back to Earth. So we have to wait a bit. But just imagine, that's the first rock sample that will ever come back. I think that's quite special. OK, and there is Perseverance, like a little celebrity, proudly looking on the 2 drill samples that we've collected. So you may ask, why are we collecting 2 drill samples of the same rock? Well, the issue is that we have 38 tubes inside the rover. The problem is, if the rover catastrophically fails, we can't extract the samples from inside the rover. That's it, the mission is over. And you can imagine that we might have filled it, and we've got no samples in 5 years' time or something like that. So what we're going to do is we're going to lay down a contingency case, an insurance case, of 10 samples currently where we are, of around 10 samples. So what we've been doing is we've been double sampling. One sample will be carried on the rover as it traverses through Jezreel and outside the crater. And one sample will be left behind in the crater where we are now as part of those 10, where if the rover catastrophically fails, at least we can send a mission that can collect those 10 rock samples. And obviously, they have to be pretty good rock samples to spend multi-billion pounds to send a mission of your money. Thank you. Just decide who it's better to give it to. All right, science or something else. It's quite easy, I think. Science wins there. Because those samples will completely change our understanding of the solar system. So that's why we have two samples, not because we wanted to produce a nice smiley face on the surface of Mars. The internet went wild. I have to say, I went wild. I was posting ridiculous pictures of big smiles on Twitter, as were other team members. Scientists are not very serious people, I can tell you. Okay, so we then drove from Citadel and drove into this weird area over here to look at these rocks, and we had a complete surprise over here. Completely not what we expected. And that's why it's about exploration. We don't go to find what we expect to find, we go to find the unexpected. And we went in this area called Seta. These are all Navajo names in this area. And these rocks over here, these beautiful rocks, these layered rocks. And for me, I'm a geologist who looks at sedimentary rocks, rocks formed at the surface. So they look like sediments. And I built amazing models of what I thought these were. I thought these were deep sea sediments. How wrong could I be? So again, here's this beautiful image. This is an enhanced color image, I should say. This is not what it actually looks like on Mars. Mars does not have a blue sky. Mars has a reddish sky, obviously there's dust. But you can see these layered rocks that look just like sedimentary rocks. And I thought these were rocks formed by deep sea flows. So here we are, drilling into this rock over here. And we did an abrasion too. When we looked at the abrasion, we took this with the SuperCam laser, which has a small camera on it. Can you see that we've got these dark grains here, these gray grains here, which are about 1 to 2 millimeter in diameter. They look like sand grains to me. So again, I thought, okay, this really shows us that we've got deep flows. And then we discovered that these were all formed by a certain mineral called olivine. Again, that's quite unusual. And then I built up another hypothesis, along with some other team members, of how these were formed from volcanoes coming out, ash beds from volcanoes coming into the deep ocean, actually, because I still thought these were sedimentary rocks. And then, with another instrument on the Abrasion Patch, they did an analysis and showed that actually these are crystals formed probably deep in a lava flow or in a big magma chamber deep in the earth. They're what we call cumulates. They're entirely what completely threw the team. It's not what we expected, and papers have still not come out yet, but it's going to throw the science community. They are really, really peculiar rocks. But what's exciting is that we've sampled these rocks. We have 4 samples of these rocks, so at least 2 will come back to Earth. Here's the Abrasion Patch over here. So these light areas are these areas with these olivine grains, and they will tell us very intricate detail about deep crustal processes on Mars, what happens in terms of convection on Mars and the mantle process, etc. So very, very exciting, and again, not what we expected. And here we are setting up for drilling. And there's our drill hole. Okay, so this shows you all the lovely samples we've collected that are already inside the rover, ready to bring home. That's about 8 samples, I believe. I can't remember. Cores 1 to 7 over here. We collected, obviously we failed with 1 sample. And this just shows you more. Since then, we've been driving to get to the delta. So I'm going to be finishing off now, but you can see the beautiful terrain over here. So these are our lava flow rocks over here. And we've got these hills in the distance, in the center of the crater. And it's interesting to think about those. We will never know what those rocks are, what those hills are made of, because we don't have time to go everywhere. A rover has a lifetime, and we also have to collect enough samples, and so we chose not to go to these hills. This hill is called Santa Cruz, and we simply have no idea. That will remain a mystery until another mission goes there, perhaps. Which is quite intriguing to think that we can have all these hypotheses, but we won't know what it looks like. But again, forms just these beautiful landscapes, austere, but really rather beautiful, and looks like a desert area on Earth. And I think that's what's surprising. I mean, I've spent a lot of time working in deserts on Earth. What's surprising to me is how Earth-like it looks, and yet how remote it is. And I think it's something to think about. So now, our main goal was the delta, and we've been having fun here. We arrived here a few months ago, and currently we are over here, just beginning our analysis, which is proving to be quite difficult, I would say. I will explain that. So during that, we actually drove very, very fast. We had this very, very long drive over here. We were driving 200 to 300 meters a day, and we were able to do that because of AI, essentially. So let's see if we can get this to work. No, it's decided. Oh, there we go. This is taken with the hazard cameras, multiple images. And what happens is this is not a directed drive, because obviously we're limited by how far the rover can see for the rover drivers to plan a drive. So basically what happens is this is automated driving. It's like your self-driving car. What it's doing is it's taking lots and lots of images as it's driving, and if it sees an obstacle, it calculates how far away the obstacle is, how big it is, etc., and whether it's a hazard to the rover, and then basically the rover can divert around the obstacle. And this enables us to drive 200 or 300 meters in this sort of benign terrain here. So if there's a big boulder or something, which we're on a collision course for, the rover will just go by it, essentially. So, and on the way, we also took this image with the helicopter. Gosh, what a lot of debris. This is actually the landing craft, crashed landing craft with the parachute over here. And a lot of debris here. So I hope we need NASA to send some litter pickers, please. I think I might start a little Twitter trend on that. Please send somebody to clear this up, so the first astronauts can actually go and clear up the mess. Obviously, that's going to happen. That's the way it is. That's space exploration. Alternative way to think about this is that this will become a tourist resort in the future, and archaeologists will study this in 100 years' time. And tourists will go and visit this as a marvel of human endeavor. If you think about it, it's an interesting concept, isn't it? The litter of the past are archaeological remains of today. Okay, so this is what we've been doing now. So we're up here in Auksbill Gap, and we did this little detour to look at this area over here. And I want to show you a picture of that. So this is a delta from a distance. This is a picture that was taken kind of this area over here, and this shows you these beautiful rocks that I won't bore you with the details of, because I could talk about them for hours. And this just shows you this terrain over here. So this is what the rocks look like, and they're quite mysterious and they're quite difficult. So these rocks over here, you can see they've got these laminations, they've got these layers in them, fine-scale layers. We're not quite sure how they formed. Either they were formed by very shallow rivers, or they're formed by currents in a deep lake. And the thing is that a single rock by itself doesn't tell us the answer. We have to look at multiple rocks in multiple places and pull together that story. It's like, again, like that detective analogy. A detective doesn't use one clue, use multiple clues to try and work out who committed a crime or whatever. And that's what we try and do. What's interesting is you can see these rocks, these are light-toned rocks, and these are gray rocks over here. So there's a difference over here between these two rocks. And so that tells us maybe the environment changed. So these might be in shallow water, and these might be in deeper water, and the lake levels grew, etc. So these are the sorts of things we try and work out. And this is the problem we've been having. So we've been having a few problems. The rocks are quite soft and thin. They keep breaking up. They're like dinner plates. So we tried to abrade this rock over here, and you can see how it's broken up over here. So we keep trying, and we'll keep persisting, but it's not. The last few weeks have been quite difficult, I would say. So we've just been doing this analysis over here. This is us about to abrade. And again, we had a failed abrasion. Well, the abrasion was successful, but the rock broke, and we couldn't deploy our chemistry instruments on that. So we're going to actually drive to this rock over here, which is a lot bit tougher, and try and analyze that. And that's going to be happening maybe starting tomorrow. So can you imagine that? Or Tuesday, actually. It's a holiday tomorrow in the US. On Tuesday, I'm responsible for the rover. I'm on shift that day. And we will be trying to abrade this rock over here. So that's the fun that's coming up. It's a day-to-day business. Okay, what's happening next after we've collected these samples? So we're collecting the samples, and we're going to leave them at a depot point on the surface of Mars, lay them out, first an insurance depot, quite close to where we are at the present day, and then somewhere further along in 5 years' time. And we're going to send a mission to Mars in 2028. This is the lander over here. which will deploy. It was going to deploy a fetch rover, but they're not going to do that now. It's going to use two mechanisms. Either Perseverance is going to deliver the rocks directly to the launcher, or there's going to be 2 or 3 helicopters. They like the helicopters, NASA. There's going to be 2 or 3 helicopters that are going to collect the samples that are left on the surface. This is mad. I trust the engineers, but it's mad. So these helicopters are going to basically have claws that are going to pick up these sample tubes. The sample tubes are that big, like a chalkboard, basically. Pick them up and fly them over to this lander and deliver them to the launcher that will launch them into Mars orbit. So there's the launcher going off into Mars orbit. There it is. And this bit then, which contains the samples, will be put into Mars orbit. And then in 2031, 32, please keep paying your taxes. That's going to be a joint NASA-ESA mission, so we can't rely on the Americans to pay their taxes. We need both. And we are still part of ESA. We might have Brexited, but we are still part of ESA. A mission will go to Mars orbit, collect those samples, and bring them back to Earth, to a repository on Earth, where they will be studied entirely robotically by instruments on Earth. And that's, of course, we don't really want to touch those samples because who knows, we don't really know what's in those samples, obviously. So they'll be contained, etc. But it's going to be very exciting because once we can analyze them in Earth laboratories, and that's not the science I'll be doing, it'll be some of you youngsters in the audience here, we will, firstly, hopefully, maybe discover evidence for life on Mars, or maybe not, and that will cause us to question, why did Earth develop life and why did Mars not develop life? So not discovering life is also an interesting question. But also, more importantly, I think, is that it will tell us the story about ourselves, our planet, which we cannot glean from Earth, because Earth has this plate tectonic cycle, and so the oldest rocks on Earth are destroyed. We don't have rocks from earlier than 4 billion years, really accessible. We have abundant rocks from that time on Mars, and they will tell us not directly about Earth, but about early history of rocky planets and about our early origins, etc. And that's going to be really important and interesting and exciting to discover and answer some of these questions. So I'm going to stop there, but I have a couple of slides of the modern environment for you to enjoy. And these are dust lifting events. Dust is really important on Mars. We've just been through a big dust storm, and we were able to record these beautiful dust lifting events on the surface. And you can see in here these beautiful dust devils dancing around the planet. It's a very active place. And finally, it's just lovely to see this image with the rover tracks as a symbol of human activity. Thank you very much indeed. It's been a pleasure talking to you.
Perfect. Thank you very much for taking us to Mars. So we've probably got time for 2 questions before we end. So do put your hand up if you've got a question. And we've got a roving mic who will come out. So yeah, can we take a question in the front here? Oh, can you use the microphone?
Do you think Mars might have subterranean life?
Yeah, I think that's a really important question. It's possible. We do have subterranean life on Earth, deep down. The trouble is we can't access this very easily, so that's a problem. So our drill only goes 6 centimeters into the Martian surface. There's a mission that was due to launch this year, but it's not now going, it's been delayed. The Exomars mission, which is a European mission, that has a drill that goes 2 meters into the surface. But we think that if there is deep life on Mars, it's much deeper down. It's difficult to access at the moment, engineering-wise.
Yeah, I agree.
Great. And I think we had a question in the middle over here.
How do you design the rover both from a mechanical point of view, but also the algorithm to ensure that it works as intended and doesn't get stuck?
So that's really outside my remit. That's what the clever engineers do. I look at the rocks. But I think many years go into that process, basically, of design, safety checking, etc. They really have just some spectacular engineers. Engineers who work on specific things. So we have a set of engineers who just work on rover arm movements. Because when we're taking some of those really high resolution images, it's really like putting your iPhone down on the Martian surface to within 2 centimeters of the rock. So if you can imagine doing that and putting it into some crevasses, etc., it requires very close movements of all the different joints on the arm. So you have to write algorithms for all of those. It's very, very difficult.
We have another question here in the front.
How long is the delay time between Mars and Earth, like the images and chemical samples?
Okay, so it takes 14 minutes for a signal to go to Mars and come back. But that time delay means that we can't really do any operations on Mars because you don't want to send the signal and then think 7 minutes later, oh dear, I sent the wrong signal, I can't do anything. So obviously with the landing, they had to do that all entirely automatically because it takes 7 minutes to land on surface Mars. So we pre-plan everything. So what will happen on Tuesday, when I'm a long-term planner for the mission. So what I do is I integrate between what science wants and what the engineers do. So I'm kind of liaison, if you like. And I will start work at about 4 o'clock afternoon, which is 8 o'clock in the morning in California. And we have about an hour and a half working with the science team, working out what we want to do, integrating with the engineers. Then we work with the engineers in deciding what the plan will be. And then the engineers spend about 2 or 3 hours checking all the sequences, making sure everything's correct with all the different instruments, because each instrument will write its own sequences, and then they will uplink to the rover. It will happen in our night on Mars. The rover will carry out all these operations, and then we get the data back the next day. And so we have to wait. So what happens is that we send signals directly to the rover, but the rover actually uplinks them to a series of satellites going around Mars. We have several. And then they are transferred through the deep space network back to Earth. So we'll get the data down the following day. So what's quite exciting is that because I'm awake earlier than California, this is the one big advantage. So I do end up working a lot of nights. So usually when I'm on shift, I'm working till midnight, sometimes 1 or 2 o'clock. I was supposed to work on Thursday, and I said, there's no way, because the last shift ended at 4 a.m., and I had somebody else come in for me, because there's no way my body can cope with that anymore. Sometimes I see the images for the first time. So when an image comes down, it might be 10 o'clock in the morning in the UK, and they're fast asleep in California and elsewhere, and the images come down, and I will go onto the site and look at the images, and I might be the first person seeing that part of Mars. It's a nice thought. It happens sometimes, and that's quite special to be able to feel that.
Thank you.
Wonderful. So I think we've got time for 2 more questions. We've got a young scientist over there in the corner, and then the last question here in the middle at the back.
My question is, how long do you think it will take for the technology to advance so you could, it would be possible for you to discover if there is subterranean life?
Oh, I think that's going to be a long, long time. I think what we're more likely to do is when we drive out of Jezreel, the crater, we're going to encounter some very, very ancient rocks that were actually formed deep down. And we hope they might contain fossilized evidence for life, microbial life, so chemical signatures. So life leaves distinct chemical signatures. I'm not an expert on that, but I'm told it does. As you have different skill sets, etc. And when we bring those samples back, we might detect those signs of of life, basically, chemical signatures of life in those deep rocks. I think it's going to take a long time. I just think it would be engineering-wise too hard to drill, hundreds of meters into the Martian surface, basically. It would be so expensive, one has to question whether it's worth it, really.
And then, we'll just take the final question here in the middle.
How much do you think it costs for the facilities for the Perseverance
Sorry, I didn't catch that. Let's wait for the microphone.
How much do you think it cost for the facilities for the Perseverance Rover to be produced?
So the rover itself cost something like $2.8 billion. That's US taxpayers, so we didn't pay for that here. And that's really to construct the rover over 10 years' time. And that's really, it's not actually the hardware, it's people's jobs, essentially. It's their salaries, paying for engineers to build that, etc. It was a little bit cheaper than Curiosity because they used a Curiosity double, essentially, so they'd already done the pre-planning, etc. It is expensive, and sometimes I'm asked, is it worth it? Is it a cost? I think you have to weigh it up against grand infrastructure projects, big building projects on Earth. So, and that's not to say that, I'm not saying they shouldn't happen, but for example, the cost of the high-speed train to Manchester and beyond is £90 billion. So that's a lot of money. I think that's money probably worth spending because it will speed up those concepts. But actually the science then is really small. And for example, the European rover, Exomars, which was spread across European countries, was $2.8 billion. So actually the science cost to the UK taxpayer was relatively small in the grand scheme of things. It's always in the grand scheme of things. And I think it's that sense of what do we discover. You know, a big part of us as humans is our curiosity and our wonderment and our trying to understand what makes us tick, and that's part of it, and I think that's important. Otherwise, one asks, what is the purpose? There's one question there.
Wonderful. Thank you all for joining us this afternoon. You've got 1 hour left of a great Exhibition Road Festival, so do certainly take a look. There's more activity here at the Society, sort of behind me, that way when you come out of the lecture theatre, but also down the road. So please do join me in thanking Sanja for talking us through Mars this afternoon. Thank you.
And I'm happy to take some questions here.